not a presentation, but something else, and I will sit over there, but it's done by Professor Nick van der Giesen, who is Professor on Water Management at Delft University of Technology, together with Nadine Rodewijk, who's sitting over there. And I give the floor to you, and you will run the show now from now on, right? From till 3 o'clock.
Thank you.
Okay.
Yeah. Yes, actually we'll start with, well, a lecture, I don't know, but at least explain a little bit about our project, which is called the Trans-African Hydrometeorological Observatory, TAHMO. And you may think, why is it such a strange, long name, and couldn't you come up with something cuter? But we actually, we like the name TAHMO because the two people who initiated this is Professor John Selker at Oregon State University and me. We both had one promoter, and his name is TAHMO, and he works a lot in Africa, so we think it's very cute, but I can also imagine that other people are a little bit confused by such a long title. Let me explain a bit what we are doing. This is a map of the world showing all the weather stations that during a certain period reported in real time to the World Meteorological Organization in Geneva. And blue is good, that means 90% or more. But green is not so good, 50%, yellow is almost dead, and the red is completely dead. So when you look at this, you notice that, well, most of the world is fine. Yeah, okay, Guinea, Papua New Guinea is a bit, could use a few more, and there's a hole in Myanmar, but in general it's okay. Except for Africa and Latin America, right? That's all. In South Africa it's fine, in Argentina it's fine, but you know, there's huge holes there basically. No observation networks. And these are the ones that feed your weather forecast. These are the stations that feed our understanding of climate change, extremes, those things. Yeah, so we know very little about these areas. Well, why would we then care about these areas? Well, there's many reasons, of course, to care about these areas, but one of them is the following. This is another world map. This is from the National Geographic, and it shows the present harvests of wheat, basically. How much food do we produce? And between now and 2050, we have to basically double our food production. Yeah, we have to produce twice as much as we do now. So if we look at this map, and we first take out the so green is sort of max, what you can sort of the max you can get, and yellow is low. So we then first take out the deserts of the world, where it's very difficult to grow food. Then we start with this, and you see these are basically green areas. Most of them are green areas. So if you take out the green areas, we say, okay, these are the areas where agricultural production is already maximum. There's a lot of competition from urbanization over water resources and space. If we take these out as well, we're stuck with two places on Earth, South America and Africa. And if we want to keep some biodiversity, it's basically the savannas around the Amazon basin and the savannas around the Congo basin. And these are basically the only places where we can really make a difference if we want to increase our food production. And you may remember from the previous slide that that's exactly the two places where we don't know anything, right? When it comes to weather, when it comes to water, because we don't have the observation station. So that's why we started TAHMO. We were frustrated by this for a long time, for all kinds of reasons, but we thought, okay, let's do something about that. But before we go to the project itself, I always have this first question. It's like, if we take then all these rain gauges that do report to the World Meteorological Organization, and we put them all next to each other, how many soccer fields do we cover then, you think? 5? Anybody more than 5? Anybody more? 5? This is what we cover. So it's about 5,000 of these things. So we're measuring, even the ones that do work, it's a very small part of the world that we cover. I once calculated every 3 trillion drops that falls on the Earth is measured. Now, you can argue, yeah, but one rain gauge is representative for a larger area. Sure, sure. But it's not, we're not really measuring an awful lot. So it's not a luxury if we, let's say, make one soccer field out of this. So that's basically the ambition that we have. We want to leapfrog. We want to make Africa the most of the best monitored continent in the world. We want to have 20,000 stations there, I mean, more than in the Netherlands, more than in the United States. But of course we have to follow a certain approach, and that's why it's interesting also to talk here and to listen to discussions here. And often people say, well, why don't you just use remote sensing or models? And yes, we have to use remote sensing and models, but you also need the ground data. Without the ground data, you are not really doing anything. That's not true, but you know, just another article came out that says that with the best models and the best observations that we have now, we cannot close the water balance for, let's say, the Congo or the Amazon within 50%. So we're just missing, we don't know, basically. So we need, and the only way forward is also through ground observations. Oops, forward, not back. Yeah, so and that's what TAHMO focuses on. Now, why are there not so many? Well, there's all kinds of reasons. One is, of course, the money. So if a normal weather station, a really top-notch one, costs about $50,000, a decent one, $20,000. That's quite a lot of money. So if you're a local government and you say, well, what do you want, a weather station or a school? Well, maybe you take a school. Not so. So the prices are high, and then it's difficult to maintain. So these networks are there. You saw this, the network, but they're not reporting. Because these weather stations that you would have here, you would are being babysat by a technician. So there's continuously someone taking care, and these technicians are often not there, especially not in rural areas. So that's another problem. So we have to come up with different designs and different approaches. This is a design I once did. This is my first and last attempt at Google SketchUp. Nadine is the industrial design. So she, so I'm a bit scared to show this even, but anyway, we don't know. We don't know what the thing will look like. Actually, we have something that comes pretty close in the meantime. But this is we need a new design, and it has to be not too expensive. Maybe $500. When we started out, it was $200. So how can we make them cheaper? Well, one of the things is that the sensors we would like to use are maybe ready-made sensors, because the volume, even though it's 20,000 stations, is, compared to a mouse or a smartphone, it's not that much. So we have to find things that are already there. One of the things is, for example, the Zytemp TN9. Who's ever heard of the Zytemp TN9? No, me neither, but I like saying Zytemp TN9. That's why I have it in there. And they come in these thermometers. So they measure long-wave radiation. And you can buy the same thing in Delft for $6,000, 6,000 euros. And this is exactly the same. And this one costs $10. Because it's mass-produced, and the other one is really a measurement instrument. You have to do some tricks and stuff like that, but exactly, the calibration is fine, it's all fine. So we have that's the way to get it cheaper, but we also want no moving parts. We want no cavities. Here you see me opening a thermometer and relative humidity sensor in northern Ghana at the end of the dry season. It's full with caterpillars and stuff and like that. That's not measuring very well amount. It's because it has a cavity. It's a nice and shaded, well-ventilated environment. And we also like shaded, well-ventilated environments, and so do the caterpillars. So everything, here you see the tipping bucket rain gauge. It's moving, so we don't want any moving parts, but that gets stuck, and there's dust coming in and whatnot. Here you see this. I like this one too. It's just a little beam with one little hole in it, and there was a whole bee colony. Oh, a bee colony. Does it have a pointer? No, but there's a whole bee colony that sort of moved in there and started living there, making themselves very comfortable. So it's really, what can go wrong will go wrong. That's for sure. And sometimes you have the bushfire. I'm not sure that we can do a lot against that, but it's the typical thing that comes. So can you make these things? Then we asked. So we asked a student, a physics student, Koen Degen, can we make something better? And he said, okay, what should I look at? So, well, let's start with rainfall. Rainfall is the single most important thing, and you will make a rain sensor today. So it's a direct consequence of this question. And he actually did better than a rain gauge. He has actually made something that enables us, in principle, although we still need to make some details we have to worry about. There are some details we have to worry about. But we can measure not only how much rain falls, but also how big the drops are and how big the drop size distribution, how the drop size distribution is, which is very nice when you have these rain sensing satellites that actually make certain assumptions about that may or may not be true. And we can test those. And when you normally would do that, buy such an instrument, you would be really paying a lot of money. The one on the left is 50,000 euros. This is the cheapest one, but that's actually not measuring individual drops, 3,000. So you spend a lot of money. And Koen came up with this. He says, take a piezometer, and a piezo element, and you'll see some. But these are the things that are typically in buzzers and things like that, that you find in the ceiling everywhere. And it costs about €1. How much do they cost these days? Yeah, maybe less even. No, we don't. And you're going to get one, so they cannot be very expensive. Huh? When you let the drop fall on it, you get a nice signal out of it, and you can actually, when a drop starts falling, it accelerates, but due to the acceleration, it gets more resistance, so it quickly has a terminal velocity. And the bigger the drop, the higher that velocity is. And you see, actually, when I started, I didn't even know, but we always, when we draw a drop like this, right? It's topped at the top, but that's not how raindrops look like at all. They're round, and if they do any change shape, they become more like a mushroom kind of shape. Anyway, they go faster and faster, so the bigger a drop, the bigger the energy basically it contains. And when it then falls on this piezo, it will ring. It will make this signal, and when you measure that, here you see the calibration curve that we have. So the dots are all smack on a nice line. It's log, but still we can basically say how big these individual drops are. Now the devil is in the details, and we're still working on some of these details. But basically, it's possible. So one sensor down, and to go. And we also realized, us bringing these into production, that's not really. We can be good at concepts, building the first one, but you have to link up with other companies. So the companies we linked up to are several, and it keeps changing. One is Decagon. That's a small company that makes weather sensors, but they have the same philosophy. They also want no moving parts, robust, but reliable, and well functioning. And I'll show you their latest design a little bit later. But also larger companies like IBM, they're very interested. They're interested in data, what they can do, numeric weather predictions and things like that. So these companies we link up with, and they get enthusiastic as well, and that accelerates our innovations. This is the latest design. And it's not yet my perfect system, basically. It does not have any moving parts, so it measures wind speed by measuring the speed of sound in different directions. It measures everything you want to measure, and the rain is measured by counting the number of drops coming through and all that, so it's pretty close, but it still has cavities, because it has a funnel for the rain to come through. So it's close, but not perfect yet. But these we'll be rolling out this year. Now, so the technology is sort of like, okay, it's very interesting. We get a lot of energy from a lot of students and things like that. It's very, very interesting. But we also have to worry about the operation. We need some money to start it up. Maybe a little bit, this is a little bit optimistic maybe, but still we need some money. And you also need some running costs. And of course you could go to a Gates Foundation and say, hey, give us 26 million, and maybe we give it. Maybe not, but that's also not really, then you put these things out there, and then what, then if nobody cares about them, then it will, they will function as long as they function, and then we just back to zero where we started. So how are we going to make, let's say maybe 2 to 5 million per year? We are convinced that we'll create a lot of value, but how do you get that value back? Or even if we get 1% of the value that we create back, we would have more than enough money to keep this thing going. Well, one thing might be commodity hedging. Yeah? So people, for example, in Ghana, people are paid up to 8 months before the harvest. They're already paid. So then when you're a cocoa dealer, you want to know how your harvest is doing. What did you buy? How is it going? Should I also go to to Nigeria to buy some more cocoa, or is it okay what I have now? So that's very valuable also for cotton and tea and all these other high value crops. And we would be able to tell better than anybody how the crops are going. Insurance is a very interesting one. Droughts, maybe also floods, maybe even diseases. And that's also taking off. So there's a lot of studies these days about insurance. This is one of the starters, the first real successful one, I would say, in Africa that's working commercially. It's what used to be called Kilimo Salama, now it's called Acre. And they run their own weather station, because how it works is people buy something, then they register it, that's thanks to mobile technology. They run their own network of small met stations in western Kenya. And then if you are within a radius of, let's say, 15 kilometers of one of these stations, and it's 10 days no rain during a critical part of the maize crop, you get paid, and they can pay people there with M-Pesa, these mobile phone payments. Started out as part of the Syngenta Foundation, but now they've spun off, and they're sort of like, they're trying to really be a commercial company. And that's very interesting, of course. And we work very closely with them together, and we hope to also roll out into Rwanda and then also Tanzania. The third pillar, so at first new technology, then we think about business, and the third one is education is very important to us for several reasons. We'd like to put these stations as much as possible at schools. So that for several reasons. One is it buys us some social protection, also some physical protection of them, because schools tend to have a fence around them. And we'd like to incorporate weather measurements into the curriculum, so that children get interested in their environment. They learn about weather, climate change. So that's important for the longer run for us, but also just cost reduction. We also work at university level. We had sensor design competitions where we asked universities, mainly in Africa, to come up with new ideas about how to make sensors that are cheaper, robuster, no moving parts. We had one 2 years ago in Nairobi, and in last August we had one in Nigeria, in Akure. And I think Kofi was there as well. It's kind of a fun thing to do, right? So there's a lot of energies coming out of that. Although practically, they could, I'm not sure how practical. Huh? They learned a lot. Yeah, they mainly came up with different ways of measuring the same thing, but then anyway. But it's just very, you get a lot of energy from this kind of teaching and working with people. And we also built a network that way of some excellent people. And we also, we're trying to build up a school-to-school program, and Nadine is doing that, where a school here buys one and pays 2 stations. One for here, and the other one goes to a sister school. And then they start talking, communicating, sharing, maybe doing farm games with each other's climate and things like that. So they learn about each other, the connectedness, what weather means for different communities. Again, partially because we're from a university and we like to educate, but partially also, again, cost sharing, cost saving. And it's not booming yet, but it may boom. We work with a company in America called Earth Networks. They have a network paid for by the schools of 6,000 weather stations. So it can work. What are the next steps? Well, we have some pilots at scale. These red countries are places where we have now some stations just to test and see how it all goes. But we have a nice project going in Ghana. We're just starting. I don't know where's Ellen? Yeah, she just came back from working on that on the a little bit post kickoff. I'm not sure, but it's very interesting. Also, a lot of interesting leads. Still a lot of work to be done, of course. And we also have one funded by USAID in Kenya, and we also hope that will also be a big success. Now you may think, well, yes, very good for these people, these technical people, making new sensors and stuff. We are never going to be able to do that. Well, the non-technical people among you, of course. But we think that you can make a sensor as well. So that's going to be the working part in this workshop. You're all going to be challenged by Nadine to build a rain gauge, a disdrometer. You want to explain this?
Yes. So now you're going to make your own disdrometer, and we're doing this workshop because we want to show you how easy it is to make such a sensor, and with the use of very simple and cheap materials as a picture frame, the piezo element, and the audio cable. So in a minute I would like to invite you to the table over here and get all the materials you need. And then first take out the glass pane of the picture frame. And then duct tape it on top of the frame. So not inside it, but on top of it. That's because if you drop water on it, then it will get stuck in the frame. Then you glue the piezo to the glass pane inside using super glue. And then lastly, you're going to solder the audio cable to the piezo, and the one part goes to the white part of the piezo and the other part goes to the metal part. I'm there to help you with soldering if you need help, and Nick is also around. And once you're done, you can come here, connect it to the speakers and test if it works. So now you can start.
All right.